Welcome to a webcast made by the Learning Enhancement team based in the Dean of Students office at the University of East Anglia. This webcast is part of the Steps into Discrete Mathematics series and concerns the basics of sets. This guide introduces the basics of sets. It is mainly concerned with explaining some of the more common terminology and notation of sets. It discusses subsets, cardinality and power sets in more detail. Introduction. One of the most fundamental topics in mathematics is the study of sets. A set is any collection of objects called individual elements or members. For example, a set can be a collection of numbers, all the mammals in the world, or the things you find in your fridge. Importantly, all the members of a set are different. So, if you have 2 bottles of milk in your fridge, you need only to include bottle of milk as an element of the set. One of the most crucial debates in mathematics was concerned with the definition of what a set was, what you can put in it, and what you could then do with those sets. These arguments were deeply philosophical and came about at the end of the 19th century when mathematicians and philosophers tried to write fundamental rules or axioms which describe mathematics. Great thinkers such as George Cantor, Bertrand Russell, Ernst Zermelo and Kurt Gödel worked towards solving many fundamental problems in set theory and gave mathematics a solid framework to build on. This study guide is not concerned with the formulation of the axioms, but a Learning Enhancement Tutor will be happy to talk to you about them if you want to learn more. The language and symbols of sets. As explained above, you can think of a set as a collection of objects. Importantly, the order of the objects in the set does not matter. A set is a collection of unique objects in any order. A set is usually denoted by an uppercase italic letter, A, B, C, and so on, and can be written as a list of its elements, separated by commas and enclosed in curly brackets, if it is reasonable or even possible to do so. Example: the set A is made up of the elements lion, cat and rat. Write this set in a proper mathematical way. The set can be properly written as A equals open curly bracket lion, comma, cat, comma, rat, close curly bracket. You can write lion, cat and rat in any order and it would still be the same set A. A set can also be defined by a rule or property which relates to a general element of that set. General elements in a set are denoted by lowercase italic letters such as lowercase a for set uppercase A, lowercase b for set uppercase B, and so on. This is a more technical way of writing a set and is usually reserved for sets of numbers which follow a specific pattern. The definition is still enclosed in curly brackets. Example: the set uppercase B is made up of positive whole numbers that are multiples of 3. Write this set in terms of a general element lowercase b. The set can be written as uppercase B equals open curly bracket lowercase b colon B is a multiple of 3, comma, B greater than 0, close curly bracket. This piece of mathematics says that the set uppercase B is made up of general elements denoted by lowercase b. Specifically, B is a multiple of 3 and also greater than 0. The colon is the mathematical symbol for such that and links the general element lowercase b to the restrictions that define the individual elements. Finally, it is also common for sets which have an obvious pattern to be written using the ellipsis symbol, 3 dots, to mean and so on. As the multiples of 3 are easy to recognise, you could write the set uppercase B as B equals open curly bracket 3, 6, 9, ellipsis, meaning and so on, close curly bracket. where it has been assumed that the pattern is easily spotted. If you are doubtful that the pattern is easy to see, you should use the more technical way of defining the set using a general element and any restrictions, detailed above. There is a special set that has no elements. This is called the empty set, or null set, and is given the symbol this, a circle with a diagonal line through it. There are symbols which denote whether something is an element of, or belongs to, a set or not. For the set A, lion is an element of A, but tiger is not an element of A. You can write this mathematically as lion is an element of A. However, tiger is not an element of A. Similarly, for the set of positive multiples of 3, 9 is an element of B. However, 10 is not an element of B. This curved E is the symbol for is an element of. This curved E with a diagonal line through it is a symbol for is not an element of. Special sets of numbers. The study guide, Different Kinds of Numbers, describes the history of how and why numbers are classified by today's mathematicians. These classifications are important examples of sets in their own right. This N symbol represents the set of natural or counting numbers. This Z symbol represents the set of integers. This Q symbol represents the set of rational numbers. See study guide, Types of Fractions. This R symbol represents the set of real numbers. This C symbol represents the set of complex numbers. See study guide, Basics of Complex Numbers. Subsets. You can choose elements out of a set to make a new set. This is because the elements you have chosen are still a collection of objects and therefore a set. This new set is called a subset of the original set. For example, you can choose the members of the cat family out of set A and form the subset C. Subset C equals lion, cat. You can write this in symbols as C is a subset of A, or equivalently, but more rarely, this. The symbol this means is a subset of, or is contained by. The symbol is a subset of also assumes that the set you are interested in can be a subset of itself. So here, A is a subset of A. The symbol this is used to mean is a proper subset of. The parent set is not classed as a proper subset of itself. The symbol this means is a proper subset of. You can use a strike through to modify the subset symbols to mean is not a subset of and is not a proper subset of. The symbol this means is not a subset of, or is not contained by. The symbol this means is not a proper subset of. For example, A is not a proper subset of A, means that A is not a proper subset of itself. By definition, the empty set is a subset of any set. So, for any set S, the empty set is a subset of S. The special sets of numbers detailed above are a good illustration of subsets. You can use the subset symbol to write that the natural numbers are a subset of the integers, which themselves are a subset of the rational numbers, which themselves are a subset of the real numbers, which themselves are a subset of the complex numbers. This tells you that each natural number is an integer, each integer is a fraction, each fraction is a real number, and each real number is a complex number. Cardinality of a set. It is often important that you know how many elements a set has in it. This is called the cardinality of a set. The cardinality of a set is the number of elements in that set. The cardinality of a set S is written as S with two horizontal lines, one either side. Example, what are the cardinalities of the sets A, C, and the empty set? As A equals lion, cat, rat, the cardinality of A equals 3. As C equals lion, cat, the cardinality of C equals 2. As the empty set is the empty set, the cardinality of the empty set is 0. Counting the number of elements in sets like these is straightforward, as they have a finite number of elements. Assigning cardinality to sets like B, which have an infinite number of elements, proves to be more complicated. The mathematician Cantor stated that some sets with an infinite number of elements have a larger cardinality than other such sets. He started off by introducing a symbol, LF0, this, to denote the cardinality of the set of natural numbers. So, the cardinality of the set of natural numbers equals LF0. And this was defined as countably infinite by Cantor. He then tried to pair up each element of the other special sets of numbers with the elements in the set of natural numbers. This can be done for the elements of the set of integers and the set of fractions, but not the set of real numbers, and therefore the set of complex numbers. Cantor worked out that the set of integers and the set of fractions have the same cardinality as the set of natural numbers and are countable, but that the set of real numbers and the set of complex numbers do not. They are uncountable. This redefinition of infinities was a great step forward for mathematics, and a learning enhancement tutor will be happy to discuss this further with you. Power sets. The final type of set that this guide discusses is the set whose elements comprise all the subsets of a particular set. This set is called the power set. The power set of a set is made up from all the subsets of that set. The power set of a set S, for example, is written P with an S in brackets after it. A good way to write out a power set is to start with the subset with no elements, then write out all the subsets with one element, then two elements, and so on until you write out S itself. Example, write the power set of A equals lion, cat, rat. The subset of A with no elements is the empty set. The subsets of A with one element are lion, cat, and rat. The subsets of A with two elements are lion, cat, lion, rat, and cat, rat. The subset with three elements is A itself, lion, cat, rat. Writing these as a set gives the power set, and so the power set of A equals the empty set, the set lion, the set cat, the set rat, the set lion cat, the set lion rat, the set cat rat, and A. You may notice that one element of the power set is a set with no elements. Three elements of the power set are sets with one element. Three elements of the power set are sets with two elements, and one element of the power set is a set with three elements. The numbers 1, 3, 3, 1 are also seen in Pascal's triangle because they are generated by the number of ways of picking elements from a set. See fact sheet, Pascal's triangle. If the cardinality of your original set is given by n, you generate the nth row of Pascal's triangle. A property of Pascal's triangle is that if you add together the numbers in the nth row, you get 2 to the power n. In other words, the number of elements in, or cardinality of, the power set of a set S with a finite number of elements, given by this, is given by the cardinality of the power set of S is equal to 2 to the power of the cardinality of S. Example, what is the cardinality of the power set of A equals lion, cat, rat? As the cardinality of A is 3, you can see that the cardinality of the power set of A equals 2 to the power of the cardinality of A, which equals 2 to the power 3, which equals 8, which you can check by counting the elements in the set, this, which was calculated in the previous example. Further guidance and information. If you have any further questions about mathematical skills or would like to discuss any other aspects of mathematics, you can talk to your lecturer or personal advisor or make an appointment to see a learning enhancement tutor in the Dean of Students office. You can telephone 01603 592761, email dos.help@uea.ac.uk, or visit our website at www.uea.ac.uk/dos/let. There are further resources on many other aspects of numeracy, mathematics, statistics and science available from the Dean of Students office and on its website. These include questions to practice, model solutions and webcasts illustrating essential skills. This guidance is one of a series on mathematics produced by the Dean of Students office at the University of East Anglia.